Hi, and welcome to Class 8. So, Charles, just before we started rolling today, we were talking about gametes. I love talking about gametes, especially when it comes to where we are on chromatic diagrams and stuff. In particular, I have a question for you, and then I have a surprise for you guys. The first question is, I went to a talk that a certain friend of yours, John, at Panavision gave. And he is a very eminent colour scientist in his own right. Now, in that, we had a triangle on the RGB chromatic diagram that said, this is the native colour I'm getting off a sensor. We haven't matrixed it yet. We haven't done anything. It's just like a kind of a camera space.
Okay.
He then said, and I just found this to be like one of those moments where the sort of light shone through down upon me from heaven.
Yeah.
He said, as you go through a matrix and you jump out to a wider gamut, that's noise. That jump is noise. If you have a big jump out to a bigger gamut, it's noise. Now, I once said that in a class, and somebody argued with me saying, that's not true. That can't be noise. And I said, well, it has to be because you're expanding out the gamut where you're going to get all that extra information from it. And so now you can resolve it for me. Was John speaking accurately, or did I mishear?
I would hesitate to criticize John in public, and I wasn't there, I didn't hear the line. But I can give you a few comments on it, and then we can talk further, or we can go into it in class. So the first issue would be that if you take a space which is digitized to, let's say, 8 bits, and move the endpoints out, and you've still only got 8 bits to digitize that, well, then the code's spread.
Yeah.
So that could be a source of noise.
Okay.
Now, typically when we're in the HD or digital cinema world, we use a sufficient number of codes that we're always below the natural noise threshold anyway. In other words, we always pick enough codes that noise is going to be bigger than one step, the natural physical noise. So that tends not to be a consideration. So part of it is true, that if you pick a larger space, you potentially, theoretically get worse noise performance. Now, another part of it is, though, that there's a big debate in the color science community about whether or not a sensor has got a native color gamut or not. And there are some people who believe that the gamut limitation is only imposed in the signal processing, not in the optics at the front end.
Because you and I have had this discussion before where we say the thing that happens in the camera is sometimes referred to some people as that the sensor, it does an RGB reading. And you once said to me, no, let's not say that. Let's just say there's a triplicate of stuff that then goes into the next pipe.
Yes, and we talked about that in a little bit in class 2, and if I remember correctly, in class 4.
Because we're going to be discussing wide gamuts today.
Yes.
And so to get back to my original question, which is if I've got a smaller triangle in my classic horseshoe, can I matrix it out to a bigger one sensibly, or is that just going to make is that a fool's errand that I'm actually eluding and fooling myself that I'm getting a wider gamut?
Well, typically it's the other way around. So there's a bunch of technical issues that are at the 800 level, which relate to how can you kind of impose a color gamut on this optical system. It doesn't really have a gamut of its own. There's a bunch of other factors that are involved, like the illuminant.
Okay.
You know, the camera head doesn't know what your illumination is going to be. So illumination obviously factors into what the colors are. But generally speaking, if you assign a gamut to a sensor system, it's pretty large. And the topic of today's class is basically shrinking that and cutting it down to a triangle that's suitable for display space.
Okay, so what you're saying is that a bigger problem is not this diagram that I saw where John went out.
Right.
It's that we've got a really big gamut, but say a Rec 709 would be inside that.
That's it. And Rec 709 is, let's call it a modest gamut. I don't want to say small gamut,
no,
but it's certainly not wide gamut.
Yeah, and it's certainly not up there with some of the others, even from its same era. Some of the print gammas, I mean, quite different, for example. And but Rec 709 is such an important one that it's worth mentioning.
It's very important, but we can consider that to be the minimum that we would go to in an HD or digital cinema production. And as you mentioned, print, Adobe RGB would be that space. DCI cinema distribution space is bigger by a good margin, bigger than 709. And the Academy effort is then leading into huge gamuts for capture, which will then reduce somewhat for post and DI and distribution.
Okay, so I said I had a treat for you guys. So if you stay with us until the end of the class, of course it's only relevant if you're in this course, I'm going to give you a question. First person to answer it in the forums will actually get an autographed copy of Charles's book.
You've heard several times already in this course that there's a requirement when imagery is captured at a really high absolute luminance level and presented at a low luminance level, there's a requirement to do a visual adjustment to the image data depending upon the ratio of that luminance to the displayed luminance. In other words, if image information is acquired in a bright environment and displayed in a rather dim environment, colorfulness and contrast seem to be lost. And if we do things mathematically correctly, it won't look right. We compensate this by what is coming to be known as picture rendering. And picture rendering is a big part of the Academy workflow, reference rendering transform, or RRT. Now, to give you an example of this process, we've reconstructed an idea that I first saw in a paper by Corey Manders and Steve Mann, both at the University of Toronto, who set up this situation, which has a camera looking at a scene, a monitor displaying that scene, all of that captured by a third camera. And I think that the idea of Corey Manders and Steve Mann was that the display in the frame would effectively be a picture inset and would reproduce the scene behind. But in fact, even from Corey Manders and Steve Mann's photograph, you can see that the colors don't match. And I think that's because their experiment was done outside. Here we've recreated their experiment, but inside, so that I'm being captured at a luminance very roughly 100 nits, and the display is producing a luminance very roughly 100 nits. So if I walk myself out of frame into the other camera's field of view, so here I am on the monitor, and I think you'll agree that this is a reasonably convincing presentation. Looks more or less the same way that it looked when I was in front of the screen. But in my view, this experiment wouldn't work if repeated at a really high light level like outdoors, which was the case with Corey Manders and Steve Mann's experiment in the photo that you saw a moment ago. So let's explore what kind of rendering transform you need to go from a really high absolute luminance level, like a daytime scene, to a moderate 100 nit HD or a low 24 nit diffuse white in digital cinema. Let's explore the visual phenomena behind the reasons for this appearance shift, and then later on, the mechanism by which we compensate for that in HD and in digital cinema. We start with dynamic range. A typical scene in front of a camera or in front of our own eyes has got a very large ratio of luminance from the luminance of the brightest element to the luminance of the darkest element. That range is typically larger than the contrast range in any particular display. Although display contrast ratio is going up dramatically and has gone up dramatically over the last 20 years, the contrast ratio of a scene is still larger. So relative luminance values in the scene have got to be compressed to bring that ratio down to something comparable to what the display can do. And some loss is incurred in that transform. And we don't do that process of reducing the range just using signal processing and algorithms. Some creative choices are involved in reducing that range as well. So here I suggest that changes in composition and exposure, even lighting, might be made to preserve some tone values at the expense of others. So there's artistic choices that fold into this reduction of dynamic range. Let's now explore the visual phenomena behind the mapping of picture information. And there's several phenomena at work. The one that we'll start with was first documented by a very famous color scientist, Bob Hunt, who wrote this up in 1952 as one of his early scientific works. He's still alive and kicking and doing very well. But in 1952, he wrote up this phenomenon by which colorfulness decreases as illumination decreases, even though the physical stimuli remain the same. My example of this stems from one of the first times that I tried to explain this phenomenon in public, which was at the IBC conference in Amsterdam many years ago. Now, when you think of Amsterdam, a Canadian at least thinks of flowers, particularly tulips. So Amsterdam is full of flowers, not in the September timeframe of IBC, but at other times of the year. And these flowers are colorful. So let's recast this in terms of your own garden, assuming that you've got flowers in your garden, and imagine going out on a very bright, clear day at noon looking at the flowers. And you judge the colorfulness, they're colorful flowers. Now, go away for 6 hours and come back at twilight. And assume that twilight involves just reducing the amount of illumination but not changing the spectral characteristics. So not an orange or a purple twilight, but just light level drop by a factor of 100. You look at the flowers, and physically their reflectances didn't change. And I've suggested I'd like you to think of this experiment with the illumination spectrum not changing. All that happens is the illumination drops to 1% of what it was. And the thought experiment is, do the flowers look as colorful? And I think you'll agree that they don't look as colorful. But now, based on the first few classes of this course, you think to yourself, the CIE chromaticity coordinates, they're the same. If you imagine where those flowers map on the U-shaped spectral diagram, they drop in exactly the same places, but they don't look as colorful. So what's going on here is that CIE XY chromaticity coordinates are giving you the physical stimulus associated with the color, but they're not telling you the appearance. The appearance depends on absolute light level. So Dr. Hunt was the first guy to identify that phenomenon and write it up in a scientific paper. So here on my slide, I give you this example of flowers viewed at daylight, maybe 30,000 nits, appear much more colorful than the same flowers viewed at twilight, perhaps 300 nits. Here's a still of me standing with a Macbeth chart in very bright direct sunlight midday in front of the FX PhD offices in Sydney. We measured the illuminance at about 60,000 lux and bouncing off a 90% reflector, that would be 17,000 nits. Here's another shot of me with a Macbeth, this time indoors at just 150 lux of illumination, in other words, a factor of 400 times less. And finally, candlelight at 6 lux the visual impression of colorfulness decreases through this series. Perceived colorfulness decreases as illumination decreases. That's the Hunt effect. So when capturing an image outdoors under bright sunlight, when displayed at 100 nits or 24 nits, we need to achieve the colorfulness of the visual sensation of being outdoors, even though the absolute luminance level is really low. The appearance transforms built into HD and built into digital cinema increase the colorfulness and increase the contrast. By default, of course, those effects are overcome in grading if you wish to achieve a particular visual look. Now, in terms of image capture and image display, this phenomenon has dramatic implications. What this means is that if you go and shoot a scene at 30,000 nit daylight, at a certain level of white, so think of a code value up near the top end of the scale, diffuse white, and you take those image data values and you carry them over to a display, and forget about gamma correction, assume that that's already taken care of, that the display has been linearized. You take this image data and you present it at 100 nits, or in my example, 300 nits, typical of a living room. Effectively, what you've done is you've scaled the absolute luminance down by a factor of 100. And that scaling down brings the scene down to 300 nits, looks like twilight, doesn't have the right colorfulness. Now, we can choose to preserve the mathematics and the physics and the signal processing, or we can choose to make the picture look right. Which do you think it is? Well, we make the picture look right because we're in the job of making convincing pictures. So to turn this image into an image that looks reasonable as a depiction of a daylight scene, we boost the colorfulness appropriately. Now, I'm not talking about zing or punch or zap or any of those sorts of words. I'm just talking about making the image look like it came from daylight. And a colorfulness boost is perhaps the most important thing we need to do. So to give the reproduction the appearance of a daylight scene, the colorfulness needs to be increased by altering the image data. So the Dr. Hunt's effect is the first of three phenomena which alter appearance on the way through the system that we have to compensate. The second one is the Stevens effect, so named after a famous vision scientist and experimental psychologist. And the Stevens effect states briefly that apparent contrast decreases with decreasing absolute luminance. So not only does the colorfulness drop, but the contrast drops. And we need to compensate that to give the displayed scene the contrast properties that you would associate with a very bright environment. Now, appearance effect number 3, I call the surround effect. It doesn't have a person's name like the first two, although you could, if you wish, call it the Bartolson-Brenneman effect. These were two researchers at Kodak in the 50s and 60s who wrote many papers about visual phenomenon in their terms associated with photography and also extending into cinema, although Leroy Demarche, another Kodak researcher, pushed that work further into cinema and then into television. And their effect is this, that grayscale tones surrounded by black are visually different from the same tones surrounded by white. And here's a visual example of that phenomenon. You can see on the left 3 squares of different luminance levels. On the right, 3 squares of the identical luminance levels, but now surrounded by black instead of surrounded by white. And you can take your digital color value inspector and look at the pixel values of that white, gray, black pair and discover that they're identical. but they look different. And they look different because the surroundings have affected the apparent lightness level of those patches. Now, we often acquire imagery in an environment where the elements of interest are surrounded by something bright. In the cinema, invariably we present imagery where everything is surrounded by black, namely, we turn the lights out in the cinema. In video, it's somewhat in between. We generally consider the surround to be somewhat dim. In cinema, we could say that the surround is black. And in HD mastering, like mastering a Blu-ray movie, we would generally do that mastering with a very dim surround, not pitch black like cinema, but quite black. So the surround of the displayed image affects perception. And basically, we need to alter the image data to dial in the amount of visual contrast that we would have seen over here in the original condition when we saw the scene in person when it wasn't surrounded with black. So there's the three effects. The Hunt effect, colorfulness decreases as luminance decreases. The Stevens effect, contrast decreases as luminance decreases. And if you like, the Bartleson-Brenneman effect, that a black surround will suck contrast out of the picture. We need to restore that contrast. The obvious question now is, how do we compensate for those effects? Well, we compensate by changing the signal processing on the way through the system. So we'd like to have an acquisition scenario where we can back out and get linear light data. That's, call it scene referred, call it scene linear, call it radiometric, whatever curves the camera apply to the data for purposes of perceptual uniformity, we'd like to undo. That's the cinema scenario. Then the compensation for those appearance effects need to happen in the DI chain. And the compensation for those appearance effects is largely the reference rendering transform in the Academy workflow, which is not yet completely standardized, and so it's another question we'll address in a later class. How did we do that in cinema up until now? But think of the Academy workflow as being a structured way to approach that problem. In video, we also apply a transform in the signal chain, but the transform that we apply is much more subtle. It doesn't show up at any particular point in the system. Instead, in HD, what we do is we do an electro-optical conversion function at the display, call it 2.4 gamma, and we tweak the gamma at the camera such that that appearance effect is overcome. So in video, and I should really say compensation for appearance effects in video or in HD, approximate first-order compensation is affected by imposing a modest end-to-end power function through the whole system. And the way we do that is basically we know we've got 2.4 at the back end. To perfectly invert that, we would have a 1 over 2.4 function at the front end, that is about 0.42, but that wouldn't do any correction of appearance effects. Instead, typically we've got a power function at the camera more like 0.5, and the end-to-end power is therefore 1.2. That's what overcomes the appearance effects associated with viewing in a dim surround at 100 nits. And the alteration of the image data is called picture rendering. And this word rendering, I'm not referring to a large bank of computers in the back room. I'm referring to rendering in the sense that an architect would use the word of forming a depiction of reality. Now, an architect would do this with colored pencils on a piece of tracing paper or art paper, but we're talking about rendering real image data, but we still have this notion of the manipulation to make the rendering look correct. And I'm suggesting there's a little bit of science and a certain degree of craft and art behind that. Now, I should back up and say that from first principles, you might think to yourself, well, I know how to increase the colorfulness of image data. That's not a problem at all. I just code the image data into YCbCr, which in the case of HD, most of the time is what the data already is to begin with. And I can just crank CB and CR gain to increase colorfulness. So why don't we do that? And the answer is, well, that would certainly overcome the Hunt effect relating to colorfulness, but it wouldn't do anything to the contrast. So you think to yourself, well, okay, we're going to have to go and do something to the contrast. We'll just do that in the Luma channel. And that would be feasible, but it turns out that an easier way is to apply a power function to each of red, green, and blue linear signals through the whole chain. So you think of linear light RGB in the scene, linear light RGB eventually ending up at the face of the display. And I'm suggesting that compensating both the colorfulness and the contrast can be accomplished by applying about a 1.2 power. Now, while R equals G equals B, that 1.2 power just forms a gentle contrast enhancement, doesn't do anything to the color. But, of course, when R equals G equals B, that's the grayscale. The effect of the power function is that if R equals G but B is different, the mathematics are such that the difference between the B and the RG will be emphasized by that power function, which will increase the chroma in the mid-scale. Now, as we approach the top end of the curve, it collapses again. And practice has shown that that overall power function implicit in video is sufficient to overcome all three of those effects that I mentioned. Now, at the end of the day, the only thing that matters really is what picture you see on the display at the completion of post and DI and VFX and compositing and everything else. As soon as you're happy with that, you're done. The whole picture rendering stuff started out really by Kodak when they made film. They knew that most of the time the film was going to be exposed in a bright environment and all of the time it was going to be displayed in a dark environment. So Kodak folded in this power function or gamma compensation for these effects into the way they designed the film. Later on in video, the gamma correction at the cameras was set at a default value that folded in that 1.2 value as a baseline. Now, the video cameraman or DOP gets to change those knobs. So you can change those knobs to make the picture look right, hoping you've got an on-set monitor at around 100 nits. And then those corrections were built into film, were built into video. It's only in the last 10 years or so that color science researchers have understood enough about appearance phenomena to start putting numbers and analysis and some mathematical justification behind these techniques that we've been using in entertainment programming, or I should say, in image capture and display of all sorts. We've been doing these corrections for years and years and years without necessarily understanding the math behind them. So just recently we've started getting a good understanding. And that understanding of the math behind the rendering, that's the heart of the Academy reference rendering transform, which is a big part of the overall Academy image interchange framework. Now, I'll close this little section by giving you a little anecdote of a certain person that I know in New Jersey who's associated with a certain large manufacturer of cameras and other electronic imaging devices. And I haven't really had a conversation with this person, but I carry around in my head the mental model of his saying to me, Boynton, you're nuts. I've been working in HD for 25 years, and you keep talking about that 1.2 power number, and I've never seen that 1.2 power in any video block diagram I've ever worked on. So you're nuts. And to that I say, well, at one level you're correct. The 1.2 number does not show up explicitly in the block diagram. And if you think in your head that a video camera does 1 over 2.2, a video display does 2.2, the system's linear end-to-end, we're engineers, we like linear end-to-end, we're done. That's one way to approach this problem. But if you look at it more carefully, you discover the Rec 709 function, even though it's got 0.45 in the equation, and 1 over 0.45 is 2.2, that doesn't accurately describe the curve as a single pure power function. If you go and do the least squares fit across that curve, it's closest to a 0.51 function. So it's almost like a square root. And if you go and look closely at the back end, you actually measure a studio reference display, or as some manufacturers call them, BVM. It's not 2.2. They measure at 2.4. Now, if you crank around with a brightness control in a consumer set, you can crank it up to a brightness level that will deliver 2.2 gamma, but that's not the typical studio case. The typical studio case is roughly 0.51 capture, 2.4 display. And the 1.2 number doesn't show up explicitly. It's just the product of those two numbers. Now, if you're tasked with taking image data which has already had those transforms done, we call that image data display referred. You're supposed to take that data and run it out through a simple set of equations to the display. The other option is to be scene referred, where you're taking image data from the scene. If you map it through a curve to get to the data, you want a simple set of equations to map back to the light levels in the scene. That's called scene referred. And there's a non-trivial transform. Well, in the case of cinema, it's a non-trivial transform in between. In the case of HD, the transform in between can be as simple as a 1.2 power function. And in some cases, we're stuck taking imagery that's already display referred, like a JPEG, but we'd really like to do some compositing or some editing or some CGI, some VFX on that image data. And I'll suggest to you that the way to do that would be to back it out to scene space, but you don't know exactly what curve to use. Your best guess is you can do something approximately a square to get back to scene space. And if my understanding is correct, I think Final Cut Pro 10, the latest rev, has got pretty much an Academy scene linear workflow buried in the guts of the signal processing. And my understanding is that when they're presented with a JPEG image, for example, they apply a power, I think their choice was 1.896 to back it out to your best estimate of scene space. And that 1.896 number is virtually a perfect match to the arithmetic that I've done. And it's simple arithmetic. It's basically a least squares fit to 709. So that wraps that section about picture rendering. And later on, in a later class, we'll talk in great detail about the Academy workflow, and the reference rendering transform is the block in that workflow that accomplishes the tasks we've been talking about. Now, we've got some time left in this class. What I'd like to do is switch to a different topic, and that topic is color primaries, old and new, moderate gamut, and wide gamut. Let's talk about wide color gamut. Gamut refers to the range in 3 space of colors available in a certain medium. And it's a reasonably easy thing to do to determine gamut of a display system. It's kind of a philosophical argument whether a camera has a gamut or not. And it's certainly true that once the image data from the camera has been rendered into display space, it's got a gamut. And you could even consider taking camera data and mapping into a set of primaries, perhaps really wide primaries. That's got a gamut. But most color scientists today are convinced that the camera does not have a specific set of what you could call optical primaries until you do the signal processing, and I certainly share that view. So gamut is a range of colors, and to a traditional old school computer graphics person or to a person working strictly in sRGB space, gamut is just a cube. It's from 0 to 1, 0 to 1, 0 to 1 on each of the 3 coordinates. That's the end of the story. But after having seen the first 2 classes in the series, you realize that gamut is really potentially defined visually. It might encompass much more than just the unit RGB cube. So we need to talk about that issue in some detail. And I should warn you right up front that gamut is completely a concept in 3 space. You should really think of gamut as being a volume of colors. In the first few classes of this course, we talked about what's in front of the camera, how you can use 3 curves to acquire that, code it into 3 signals representing vision. You could jokingly refer to what happens in front of the camera as 31 space, that being the color space from 400 to 700 nanometers divided into 10 nanometer chunks. So gamut does not live out there in 31 space. Gamut lives in 3 space. And properly, you should really measure gamut in cubic units of something. But I have to warn you that a lot of displays are specifying gamut coverage in terms just of an area in the XY chart. And the area of an additive RGB system is a triangle. That's not really an adequate description, and we'll talk about why as we go through this part of the course. Now, this slide shows you some data replotted by me, but the data originates from a 1976 paper by a Kodak England researcher named Mike Pointer. And he simply, and I say simply, it's a little bit like Newton's experiment, it's a lot harder than it looks, but he simply took a colorimeter or a spectral device, but he mapped the data into color coordinates, and he measured somewhere between 1 and 2,000 objects that he found inside and outside lying around. So in some sense, they're natural objects, although he's including pigment and paint. But he's not including fluorescent colors. He's not including weird sources like lasers. So he took all that data, he did a bunch of computation, and he tried to form what today we would call the convex hull of those measurements. Although, well, this hull isn't particularly convex, but this is a shape that I've drawn around his data. So in a sense, you could think of this as being the gamut of the real world colors that you're likely to encounter that are likely to be in front of a camera. And I've plotted these in L star, U star, V star coordinates, which you'll remember from class 3 have got a range L star 0 to 100, U star, V star approximately plus minus 100. So very roughly, well, here you can see it goes as far as 150 and doesn't quite reach minus 100. But very roughly speaking, you can think of my coordinate system as having 4 million coordinate points. And maybe we've only got pi over 4 times that because we've got a blob in the middle. The important part about this slide is it's a blob. There's no simple, regular geometric boundaries around the colors you're liable to encounter in real life. Now, A committee of the CIE took Pointer's 1976 data and replotted it now in A star B star coordinates, but still, roughly speaking, plus minus 100 on A star and B star and 0 to 100 on L star. And superimposed upon that plot, the sRGB cube, which are the colors that a traditional computer graphics person or a desktop graphics person might think are all of the colors. And now two things I'll point out. One thing pointed out on the way. I said sRGB cube, but straight lines in big X, Y, Z, and straight lines in little x, y chromaticity, and straight lines in U prime, V prime, they all map to straight lines as you go from color system to color system to color system. But when transformed to A star, B star, they're no longer straight lines. So it started out as a cube, but it gets plotted in A star, B star as lines that curve. Nonetheless, I'm sure you very easily see the cubic shape that underlies that. And the other obvious thing that you see now is that there's regions of Pointer's real-life colors which lie outside the capability of sRGB to reproduce. And there's also completely reasonable sRGB colors, such as up here, which are outside of the colors that you would encounter in real life as documented by Pointer. And whenever you have two different media, even the media of the real world in front of the camera and the media of the display system that we're targeting, there's likely to be a mismatch. And so somehow you've got to do gamut mapping. Now, if you start out with a scene that has only got a set of muted colors, it's possible that all of those colors would map into legal, meaningful sRGB or 709 coordinates. But the more typical scenario is that you shoot something that has quite highly saturated colors, or if you wish, highly chromatic colors. They may end up being out of gamut, that is, delivering 709 RGB numbers bigger than 1, or the even weirder case, less than 0. Because there's certain places here, and this will become more clear when we show the triangles in a moment, certain places where you can only get to a highly chromatic cyan color by sucking red out. And that sucking red out corresponds to an R prime value that's less than 1. Now, you can plot these gamut maps in various coordinate systems. I'll show you yet another coordinate system. This one is plotted by my colleague Chuck Harrison, who was examining the gamut of motion picture print film in the early days of the DCI effort. And his chosen color system is U prime, V prime. And in the U prime, V prime space, it's a projective transform of little x, little y, so straight lines stay straight, but the projective transform maps an additive RGB system into a triangle. And here he's plotting luminance, or actually log luminance, on the third axis. So the triangle here that forms the bulk of this shape is formed by the vertices of the three primaries that he's using, in this case, 709 primaries. And the patches here, yellow and brown and dark brown, are patches pulled from data of motion picture print film. So the lesson here, and we knew this already, motion picture print film has got a wider gamut than 709. So in the early days of digital cinema standardization, the technical experts at the DCI, including Chuck Harrison, including me, including 24 experts from the studios and manufacturers and other places, that group identified the need to standardize an RGB system for the display of digital cinema wider than 709. And in a few moments, I'll show you that diagram in a CIEXY chromaticity chart. But for the time being, I want to reinforce to you the point that I made in class 2, that you should always think of that chromaticity diagram as having a third axis, even if it's not drawn on your chart. And Chuck Harrison has given us this drawing that includes the third axis. Now let's walk through about 6 additive RGB systems, all of which are important at some place or other in the video HD D-Cinema chain. We'll start with NTSC 1953, which is obsolete. And I explained early on in the course that it's obsolete because the original 1953 green phosphor was slow and dim. And as the receiver manufacturers felt the demand to get rid of the green moving trails and to make brighter receivers, they changed the phosphor. And that change in phosphor resulted in the green primary moving from a very highly chromatic green to a less chromatic green and closer to yellow. So this is the chromaticity diagram from 1953, abandoned by about 1960. In fact, abandoned almost before the videotape recorder was invented. So roughly speaking, nobody ever coded digital image data using these primaries. Now, it's a bit of a problem that these primaries show up in all the textbooks and they show up in menus for choosing color systems, even in Photoshop. And you might think, oh, I'm in SD, I'm doing an SDTV production, I'm in North America, so I know we use NTSC, so I'll pick NTSC. That would be wrong. You need to pick a different system, which we'll talk about in a moment. Now, I'm going to skip 2 systems, SMPTE and EBU. Those systems were standardized, the EBU standard in about 1970, and the SMPTE standard took another 15 years, actually 1985. Those are the standards for SD. They were slightly different. They both had green moved in. I'm skipping them because that's just SD. And HD was standardized in 1990, and digital television is supposed to use the HD primaries even when transmitting SD digitally. So we should now just move forward into the 709 era corresponding to the HD standards. So here's that map, and it's just this particular set of red, green, and blue. They're highly standardized, widely deployed, and use them for SD, use them for HD. Now, there's certain reasons we'd like to have a wider color range. I've already mentioned digital cinema projection. Graphic arts really needs a wider color range. And for capturing images, we'd like to capture those into a color space wider still to give us some latitude in post-production and DI. So we get to those in a moment, but we'll use this 709 triangle as our reference point on that journey through the rest of color space. Now, the problem with 709 is there's lots of interesting cyan colors over here, which cannot be coded in 709, but they can be printed very easily on either an inkjet printer or in graphic arts offset printing in a transit shelter, poster ad, or all sorts of important industrial applications. And so we'd really like to capture those colors in a graphic arts standard. That's what Adobe RGB 1998 ends up doing. Also, there's a bunch of deep reds, scarlet if you like, orange, and yellow, like Kodak yellow, which is missing from 709. We really can't get as yellow, or if you wish, gold, as you'd like to get. So we'd like to push the boundaries out on this side as well. Adobe RGB basically has 709 red, 709 blue, and a green which is exactly literally the original 1953 NTSC green. Now, NTSC red and blue were a little bit different, but it's almost exactly the case that Adobe RGB mimics 1953 space with its wide green. Now you can immediately see from this diagram that Adobe RGB has managed to go capture all of those cyan colors. And that's a good thing. But it doesn't have any significant improvement in the deep reds, the oranges, and the yellows. And it's widely used in graphic arts, but for cinema, doesn't cut it. For cinema, we need to go get these colors. And the only way to do so is move the red out. And then, well, we'll have to decide where the green goes. But if we simply move the red out to the spectral locus, we're going to capture those deep reds, oranges, and yellows, or golds. So here's the SMPTE DCI P3 primary set. Just move the red way out. The green is not the same as 709. It's not the same as Adobe RGB. It doesn't have the same sort of improvement in cyan that Adobe does, but this is not for graphic arts. It's for digital cinema. It was chosen to be a very good match for graphic arts. Now, for digital cinema, on the distribution side, the community making these decisions was concerned that they didn't want to restrict the distribution color space by the display technology of the day. So some very long and complicated discussions were held concerning what would be a good future-proof standard to choose for distribution. Some of the participants in that discussion were adamantly opposed to metadata. Even though you think we could relatively easily just drop into the data stream the RGB XY chromaticity coordinates and then interpret them on the way out, some of the participants in the committee work didn't trust metadata, period. So the agreement was reached that the DCI distribution scheme wouldn't have metadata. The imagery would simply be coded in CIE big X, big Y, big Z space. So we know what, well, the primaries, if you want to give them little x, little y numbers, are 1, 0, 0, 1, it's off the screen, and 0, 0. So if you want to think of it as RGB, those would be the coordinates. But because the coordinates are all just ones and zeros, you don't need metadata. This is the distribution scheme, and at the back end of digital cinema, basically as part of the packaging exercise, you package it into that container format. Now, everyone today, and I think for the foreseeable future, will be mastering in P3 RGB space like I just showed you, and then only as a final step, coding into XYZ space just for transport. And the first thing the projector does at the back end is unpackage and code into P3 RGB, because that's what the projectors do.
Okay, so I said at the beginning that we'd give away a copy of, well, you know, it's very generous of you, Charles, an autographed copy of Charles's book. So the question we have come up with is something that you can actually find out in Charles's book, but it's going to be a little bit of a history exercise. Charles, what's the question?
The question is, in what year was the original color television gamut standardized?
Okay, so this is the first time that somebody was moving into colour. So we're not talking about something in the last couple of years. This is more of a history thing.
But it's a gamut question because
Absolutely,
it establishes a triangle.
Yep, and that's a very important gamut, and there have been other ones since, but that one was a big one for us. Okay, post it in the forums, which is probably the easiest way to do it. And actually, you know what? I'm going to get you to email it to me, Mike S. at fxphd.com, and then I'll know which I got first, because otherwise we get time-stamped in the forums. So Mike S. at fxphd.com, and then I'll pass on to Charles who won, and then wherever it is in the world, I'll pay to send it to you. Thank you, Charles.
Great. It's a pleasure.